I can think of at least two reasons. One, because they were designed or built badly, and there's heaps of pictures of walls like that on my website. The other reason, the second reason, is the one that this clip's about, and that's because we don't want them to be watertight. What? Why on earth would we want our walls to leak? Well, let's think back to that raincoat analogy that we used in the discussion about deflection, right? Raincoats are like the outer skin of our buildings. We want them to deflect water. But there is a distinction here to be made between roofs and walls. Roofs are like plastic rain caps, really. We want them to shed water. But walls are a little bit different. Of course we want them to shed water, but we don't need them or want them to be as waterproof, as completely waterproof as roofs. Think about plastic raincoat. Now imagine wearing that plastic raincoat next to your skin. Now we all know what will happen if we wear a plastic raincoat next to our skin for any period of time, right? And why is that? Yeah, we all sweat. In fact, the water vapour that our bodies give off, if we could see it, it would be like an aura surrounding us, like clouds emanating from us all the time. We can't see them, but that's actually what's happening. And this brings us on to a brief discussion about water in its various forms. We're familiar with three different forms, right? Solid, liquid and gas, like this. Beautiful shot, eh? See that water vapour coming off the top of the ice. So the way I think of water vapour is like H2O molecules just zipping around in the air all the time. And the warmer the air, the more excited these little molecules get, and the faster they go, and the more of them the air can hold. So the warmer the air, the more of these little molecules the air can hold, and the faster they go. Conversely, as the temperature comes down, as the air cools, it can't hold as much water vapour anymore. If you can just imagine shooting a gun, what happens to the bullet at the end of its flight? It starts to come down, right? In the water molecules, it's like they become lethargic in the cold. Something we can all relate to. They fall out of air eventually, and that's what we see as condensation that we're all familiar with. And this doesn't just happen on glass. I mean, we see it inside the house too, like this. And it's the same process in each case. All that's really happening is that you've got the coming together of two bodies of air that are at different temperatures. So when you bring that glass out of the fridge and you grab your steiny to watch the All Blacks, the air right next to the bottle, not next to the container, that's become much cooler than the air out here. And so the molecules that are zipping through, when they enter that cold space, they fall out and they condense onto the glass. This is another classic example. So the only difference here is that one pane of glass is insulated and the other one's not. One's double glazed and the other one's not. So that double glazing provides this insulating buffer, which means that you don't get that juxtaposition of hot and cold air within the same room. Cold air is on this side, the warm air is on the other side. Whereas with the single pane, the cold comes right through, so you do get cold air and hot air in the same space, so then the molecules fall out when they jump from one space to the other. That's pretty simple, isn't it? Maybe that's too simple. I mean, there's one other thing that we haven't talked about, and that's the fact that glass, like plastic, is completely impervious. So the water molecules just can't get through it. You know, no matter how fast they're going, they just can't get through the glass. So now you imagine your wall, the outside wall of your house, right? So let's say it's a wooden wall. You've got a wooden structure and you've got plasterboard lining on the inside and you've got some sort of cladding on the outside. Now imagine putting an impervious layer of plastic somewhere in that wall. It doesn't much matter where you put it, just imagine putting it somewhere, and then imagine what happens to the air. You know, on outside, temperature goes up and down. Inside, much less movement in temperature. And so inevitably you're going to get differences in temperature on either side of that plastic layer. And now we know that as soon as you've got cold air on one side, can't hold the water molecules up, they fall out and you get condensation, which we call interstitial condensation, which is just a fancy word for within spaces, so in this case within the wall space. So we don't like that. We had a bad experience in the 1980s in New Zealand where we had a plasterboard lining that they produced with foil on the inside, just a very thin layer of silver foil. It was supposed to stop the temperature transferring through the plasterboard, which it did a little bit, but what it did really well was to stop the water vapour. And so you had a difference in temperature on either side, impermeable barrier, bad news, condensation forming, interstitial condensation, water vapour within the walls condensing out. So we try to avoid that, and the way we avoid that is by making our walls breathe. So that's the explanation for why our walls leak. They leak water vapour. We try to make them waterproof to resist liquid water, but we want them to allow the transfer of water vapour. However, if you think back to that conversation that we had about deflection and drainage and drying and durability, if not all the water escapes, or if it does condense out, wouldn't we want that to drain away freely and to dry out easily? Worth thinking about, isn't it?